All right, folks, we are heading into section 6.3. Now we're going to start talking about integrals and an interpretation of what the integral actually means. And that is going to be related to area. It's actually we're going to make a case that it's measuring or it's calculating area. And what is called, now we've been talking about the indefinite integral, and this is going to relate to an idea of what is called the definite integral. I never really explained what is it that makes the integrals we've been doing indefinite, and we're going to take a look at that first. So I didn't explain it because I had to. It would be hard to explain without talking about what the definite integral is, what the difference between indefinite and definite, and I wasn't ready to talk about the definite yet. Okay, so now it is time to say, okay, well, Mick, what did you mean? What does the author mean in saying, okay, this is an indefinite integral, this is an indefinite integral, and that's the only kind that we've been doing so far. Okay, so we're gonna try to set the table there. All right, so now if I've got a function and I know its derivative, what we've been seeing so far is that if I know the derivative and I do this operation called taking the integral, calling integrating, looking for the antiderivative, we saw that this ended up being equal to the function. And then we had some arbitrary constant that we needed one more piece of information if we were going to nail down what that constant was. And as we've been doing the past couple lectures or so, we've been looking at that particular issue in there. And so this is an indefinite, right? So this right here is an indefinite integral. And it's not definite because if you think about it, okay, we needed one more piece of information to know what this constant is. So there was an indefinite feel to it. It was, we definitely figured out what the function was itself, how in terms of what its derivatives would look like. But we didn't know how far up or down on the graph it was shifted. So it was not definitive. We knew a lot of information about it. We didn't know everything about it. All right. So it was indefinite in that sense. Okay. So now here's one thing that we're going to notice here. Okay. So this might not have occurred to you, or maybe it did, but if you were to take that same function, right, f prime of x, and you were to integrate it, do an indefinite integral on it, and you were to evaluate it at a particular value of x, like this, and you were to subtract off that same function, integrated, right? So function f, and you were to subtract off that function evaluated at x equals a. Okay, so what I'm trying to get across here is, let's suppose I were to calculate my indefinite integral and I would evaluate the at x equals b, and I would do the same and then evaluate it at x equals a. All right. Now the indefinite integrals, these two are the same. All right. So what I'm saying is that you might look at this and go, wait a second, isn't that just zero? And I'm saying, no, let's take the derivative, let's plug in x equals b, and then let's take the integral, and then let's get the integral again, and let's plug in x equals a, and let's look at the difference. All right. Now, if I say, okay, this is f of x plus c, this is also f of x plus c, but if I plug in x equals b, I will have f of b plus whatever that constant is, minus, and I should put a bracket in here, f evaluated at a plus that constant. Now, if I take a look at that and I subtract that off, the constants are actually going to cancel out. All right, so because this will just end up being equal to the function itself evaluated at b minus the function evaluated at a, like this, and the constants will cancel out. See, that negative sign distributes, and the c cancels out. And so now this is what we are going to define. So I'm going to put 3 lines in there saying it is defined as being, so what I just did mathematically there's a shorthand for that, is that if I take the integral of that f prime function and I want to represent, okay, this is the difference between it evaluated at b and a, what I do is I put some little endpoints in here. You can almost think of this as an interval, and we're going to see that it makes sense to think of it that way. in going from A to B, that this is defined as being the integral of f prime with respect to x, is that this is what we call the definite integral. So notice the constant actually goes away. Okay, so this is what's called the definite integral. And we're going to be doing a lot of calculating of definite integrals in here. But before we start doing lots and lots of integrals that are definite, we want to start talking about, well, okay, so what? What does it mean? What is it telling us? And there are a lot of different ways to interpret it. There are a lot of different ways you can use this. But notice, but before we go on, just notice that the constant then doesn't matter. Constant gets subtracted off. So I don't ever actually, if I'm worrying about the definite integral, I don't actually have to know what that constant is. That comes out in the wash. All right, so first thing we want to know, or want to pay attention to, we've got this new thing that is, or this twist on an old thing, the indefinite integral. But if we put some endpoints in there, so x equals b, x equals a, and we think of it as a difference, constant goes away, and it is a useful mathematical tool that we're going to see what it does, that we call that the definite integral. Okay? So it's still an integral. It's just that by taking that difference between those two endpoints, I don't care what the constant is, right? But then the question is, well, what does it mean? What does it actually tell us? And the first interpretation we're going to have is geometric. It's going to tell us an area. All right, so let's take a look at an example. Let me say, well, let's suppose, let's start with something really simple. Let's suppose that my derivative is just equal to 2. All right, so if my derivative is equal to 2, and I were to graph out this, so if I were to plot, now I'm not going to plot f, because you might be looking at this and you're saying, okay, if I take the integral of this, I'm going to get a line, because that's a constant slope. Okay, what kind of functions have a constant slope? All right, so this definitely is the answer to this. If you were to integrate it, the function is indeed a line of slope 2. Wouldn't know what the intercept is. But here I'm going to do something a little funky. I am going to plot out what the derivative looks like, what the graph of the derivative, what the graph of the thing inside, by the way, so what's inside, by the way, we'll throw a little vocabulary in there, that what the integrand is. All right, so I'm graphing out the integrand, and let's see, I'm going to do that in red. All right, so f prime of x equaling 2. All right, and so if I were to plot that out, that is just a horizontal line, like so. All right, and I am going to worry about an interval from 0 to 3. All right, and I'm actually setting up these little endpoints. These are going to, we're ultimately call these our limits of integration. And I'm going to consider what's going on with my derivative, what's going on between 0 and 3. Okay? And so if I were to plot that out, I have 1, 2, and 3. Here I got 1 and 2. And so what I'm worrying about is this part of the graph, right? So I've graphed out my derivative, the function that I'm starting with, and I've looked at what its graph is, and it says, okay, here's x equals 3, here's y equals 2. That, by the way, is not a negative. That is just the line going across. I should have drawn my 2 a little bit above there. All right, and I'm going to worry about what's going on from 0 up to 3, x equals 0 up to 3. All right, now, if I just very, without thinking too hard about it, and just say, okay, I want to learn how this is done. And I were to say, let's take the indefinite integral of it. I would write this out, and I would say, okay, I'm going to take the derivative, it is 2, and I'm going to integrate it up. So I'm going to take this function here. This integrand is going to be what I've got up here. And I'm going to consider the value of this definite integral by considering going from 0 to 3. So before, we didn't ask the question, or is there some interval we're worried about? This one, I'm worrying about some restricted interval, some closed interval, 0 to 3. And when I take that integral, right, the integral of this would be 2x. Now here's the new symbol. I'll do this in green. All right, so notice that I put my endpoints of my interval 0 to 3 like that. And after I take my integral, instead of writing plus c, I am going to put a straight line to the right. And this is telling me, this is reminding me that I am considering the definite integral from x equals 0 to x equals 3. I'm considering this closed interval right here. And if I go back and look at what my definition is, that is telling me that I am taking 2 or taking 3 and plugging it into my answer, and I am taking 0 and plugging it in, and I am finding the difference. So this is f of b, this is f of a, where b is 3 and a is 0, like that. And so I end up with a value of 6, right? And you might say, so what? Okay, so that's 6. All right, now here is another thing I want us to notice. I'm saying, notice that, right? 6 is the area under the graph of my integrand. Right? So look up here. What do I got? I got a rectangle, and it has one side is 3, one side is 2. And so notice that the area that I mapped out here that I shaded in, so we call that the area under the graph, going from the graph down to the x-axis, that's a rectangle of sides 3 and 2 that has length times width, area is 6. Right? And what we're going to see is that that's true in general. Okay? It's easy thing to look at and see that it works with a with a constant horizontal line like this. All right, so let's put, and this is going to be true in general. But let's try it with a little bit trickier. But I don't want to get too tricky. But let's try it with a little bit trickier function in there. So I am going to now. So let me notes here. All right, so let's go ahead and I am going to take a look at what if f prime of x is just equal to x, right? So now I'm make it, I started with a constant. Now I'm just going to make it kind of simple, but it's going to be a little less trivial. So that if I were to graph out what my integrand looks like, this, I would have, all right, so if I'm going to go do this in green, how about it? So I'm going to go 1, 2, 3, and I'm going to go 1, 2, and 3. And so this is going to be to graph out this function. It's a line of slope 1 and has intercept of 0. So it goes through the origin. And I am going to again consider a closed interval from 0 to 3. All right. Now, the reason I'm starting with something simple is if I were to say, all right, so if I'm going from here, x equals 0 to x equals 3, there is an area that is contained under the graph. So there, in red, I've put the area under the graph. Okay, so, all right, now if I do the indefinite integral for this, I am going to take the integral from 0 to 3, so over an interval from 0 to 3, and my integrand, my f prime up there, is x. And so if I integrate that, and it's a definite integral, and nice thing, when I'm doing a definite integral, I'm not thinking about the constant. I don't have to worry about it because by doing that subtraction, it goes away. But the answer to this is 1/2 x squared. And using that new symbolism, I am going to go from 0 to 3 like that. So that straight line over there is reminding me that I am doing a definite integral over the closed interval from 0 to 3. And so the answer then, when I go and I take those endpoints and I plug in, I take the number up here on top. So that's going to be 3 squared. So we got 1/2 3 squared like that. And then I'm going to subtract off the value of the function when evaluated at the other endpoint. In this case, it's just nice and neatly 0. Right, so what have I got here? I have got 1/2 times 9. Oh, wait a second. This is 9/2. This is 4.5. Okay, so 9 halves, 4.5, however you want to look at it. Okay, now if you look at the area of this triangle, we've got a 45, 45, 90. So this is, we've got these two sides are equal, these two angles are 45. And this leg of the triangle is 3, this leg of the triangle is 3, and this is half of a box, right? So actually, I should say half of a square, right? Right. Well, square with sides of 3 has an area of 9, and we are only including half of it, right? So square would have an area of 9, and wait a second, half of that square bisected like that, my area would be 1/2 of 9. Wait a second, 4.5 again? The answer is yeah, it is also 9/2. Okay. Now, with these two simple examples, we could actually just very easily calculate what the area is. All right. Now, where it gets trickier is if we have something with some curvature to it. Right. So with the constant, we just had a rectangle. With the line, we just had a triangle. And those are one areas we can just calculate by hand, no problem. Right. Now we're gonna up this trickiness of this a little bit. But so I'm even gonna phrase it like that. I'm gonna say that this gets trickier with trickier functions. Okay, how is that for brilliant, huh? It gets trickier with trickier functions. Doesn't that happen with math in general? And usually it does. Maybe the derivative of e to the x is the exception to the rule. But if we had a function such as x squared, a parabola, and we wanted to consider that over some closed interval like 0 to 3, if I were to plot this out, I'm going to do it cartoony to start with. If I were to plot out f prime of x and versus x, this is going to be parabolic in shape. Right? And so if we were to try to calculate the area under this particular curve, you can't just simply use the area of a triangle. You can't just simply use the area a of a rectangle in there. So this actually gets okay. This all of a sudden now brings in some complication. All right, so now and so this, by the way, this indefinite integral stuff does work in general. I encourage you, if you got your book, you might actually pause and go and look at page 435 because it talks about how this works in general, and kind of follow along with what's going on in the textbook in there. Okay, so I can't just readily calculate the area of that. That's kind of tricky. This has got some curvature to it. So there's not a nice, neat triangle. There's not, there's not a nice, neat rectangle in this. And so, but what we can do with this is we can approximate using, here I'm going to use the word boxes. All right. So we can approximate using, and I put in quotes, boxes. All right. And here's what I'm thinking with this. Okay. So I'm going to draw this. I'm going to do this very cartoony as well. All right. So I'm going to redraw my graph. And I'm going to try to get this across conceptually to start with. So I've got this curve, parabola in this particular case, as an example. And there is, and we're going from one endpoint to another, right? So we're considering the area under the curve. And so if I were to go from 0 to 3, okay, so I'm going to draw a little dotted line here like this. All right. If we were to try to approximate this, what we could do um, is what if we broke this up into three different boxes? So if I had one and two like this, all right. So if I were to break this up into three different boxes, I could say, okay, what if I were to draw a little rectangle that goes like this? Draw another rectangle that goes like this, and draw a third rectangle like this. Okay. So can you visualize that? These should imagine these being perfect rectangles in there, but definitely check out your author does similar thing in the textbook. But you see how here's a rectangle that has some area. Here's a rectangle that has some area. And notice I've kind of overshot over here and undershot over here. And here's another rectangle that is, that approximates the area under the curve in this part. So again, overshoots a little bit, undershoots a little bit there. Now this would be an approximate. If you take the area of these three rectangles, if you were to figure out what the lengths and widths of these are, you were to look at them, you'd say, okay, if I were to add up this area plus this, I would actually get an approximate value for these. All right, so now, and point out, so use more boxes and you get a better approximation. Okay, so stop and ponder that. Think about this. Okay, it's boxes. All right, so I'm trying to calculate the area under this curve, under this graph, and I don't have a nice, neat triangle. I don't have a nice, neat rectangle. But if I take a bunch of rectangles and use them to approximate the area under there, I get a value that'll be close. And the thinner I make these, the skinnier I make these boxes. So the more of them that I use, the better my approximation. Right? So let's take a look at that in action. Okay? So this, by the way, what I'm telling you right now, this is the concept of what is called a Riemann sum. And Riemann was a very, very accomplished mathematician who came up with this way of thinking about what definite integral is telling us. So this is the concept of a Riemann sum. So this is the summation. Here's my pen, okay? So if I'm adding up each of these areas, so I'm adding things up in here, and I'm adding up areas in there, and that's the concept of the Riemann sum, in that if you've got a function, any function that has some funkiness to it, and you wanted to get the area under the curve, and there actually are legitimate reasons in mathematical analysis that you would like to know what is the area under the graph. Basically, if you take a whole bunch of rectangles and you approximate the area by finding those rectangles, like that. All right, so got rectangle 1, rectangle 2, rectangle 3, rectangle 4, rectangle 5, rectangle 6, etc. Okay, so you guys ready? Here's where we're going to talk some calculus in here. All right, so this is the concept of a Riemann sum, the idea of breaking up the area into these boxes that will approximate the area under the graph in there. And in the limit, so the question, if we are in class right now, we're in lecture, I would say to you guys, all right, what's the most number of boxes that you could put in here? How many boxes could you put in there? And eventually, actually, someone might chime in right away. Okay, so the most is in the limit as you head towards infinity. So in the limit that the number of boxes say approaches, goes towards infinity, the area, see, I'll do this in green, that area under the curve is a from A to B. All right, I'm going to call this Y. I'm going to call this X. That if I want to know the area under the curve of Y and I integrate over X from A to B, the indefinite integral is indeed the sum of those boxes in the limit that the number of the boxes goes to infinity. All right, so this little curvy S thing, this integral, that is a summation. It's made to look like an S for purpose. It is telling me that I am adding things up. I'm adding up all the boxes from A to B, and the width of each of those boxes is dx. One of what one of the questions that was asked in lecture was, what is the meaning of dx in here? Does it tell us anything? And that is actually the width of your box. And if we were doing a finite, we would just have the width of it be delta x, distance from here to here. And so this dx actually represents the width of your box. And then this is your height of your box. So dx is the width of your box. Y, the value of the function, is your height of the box. So look at what you're doing. This is, basically height times width. So this length of this side of the rectangle times this side. So wait, that's the area of the rectangle, and we are adding up all the rectangles from A to B. In this case, how many of them are we adding up? If we do the integral, we're adding up an infinite number of them, which means that actually the little width in there has shrunk down to what's called infinitesimally small. These boxes are basically a whole bunch of lines, and we're adding up an infinite number of those lines to actually figure out what the area is. Ponder that. That is the basic idea of the area interpretation of these lines of these areas of this indefinite integral. It's telling us the area under the curve, and we can actually extract a lot of information out of it. In physics class, we use it to calculate a quantity that is called work. It's the amount of energy that is put into a system. But there's all sorts of applications for this. And unfortunately, we're not going to, we're running out of time in the semester, so we're only going to be able to scratch the surface. But we are going to be able to get some mileage out of this. We're going to be able to get do some substantial calculations. Okay, so now let's put this in action. Ponder this. Try to get this clear in your head. But let's say we had a situation where this is going to be my integrand. Notice I'm not writing it as f prime anymore. I'm just saying, okay, what if I have a function y is equal to 4 minus 2x? Okay, so that is a triangle. All right, so now I'm doing this because I want to do an approximation. Now the triangle I could actually calculate, but what I'm going to do with this is I am going to approximate, and so I'm going to go. I didn't give you an interval for this. I'm going to consider from 0 to 2, and I am going to approximate, right, with two Riemann sum, RS Riemann sum boxes. Right. Now with a triangle, I don't have to do that because the triangle, we can do the calculation, but I'm going to start with something where I know the answer. All right, so there's x, there's y. All right, so 4 minus 2x, what that would graph out like is if I were to go 1, 2, 3, 4. All right, so 0, 4 is a point on the graph. The y-intercept is 4. All right, and my slope is -2. So if I were to do 1, 2, 3, 4, like this, I go down 2 and over 1. So I go down 2 and over 1, down 2 and over 1, like so. I've got, let's see if I got a straight edge I can use here. All right, so if I were to draw that, like so. All right, so there's my Here's my graph. All right, now I'm going to approximate this as a Riemann sum. All right, so indulge me. I'm going to draw my graph again, and I'll make it make it a little bit bigger. And so if I were to take this and say, all right, I've got this graph that is looking something like this, right? And what I'm going to do is I'm going to break it up into. I said that I was going to do it approximate. Okay, and I said it and didn't write it with two Riemann sum boxes. Right. So now it's kind of silly for me to do this because I can calculate it, but my reason for doing it is I want to show you how does this work? How do you think about the approximation? Right. So I'm going to break this up into two boxes. So here's 1/2, here's 3/2, and here is 2. All right. So I'm considering from here to here. And my boxes, what I'm going to do is my first box will go from 0 to 1. My second box will go from 1 to 2. What I'm going to do is I'm going to draw my box in such a way that where I cross through the line is going to be right at x equals 1/2. Now, I didn't do a great job of drawing it that way, but this is meant to line up. So I've drawn my box because I want to overshoot a little on this side, undershoot a little on here, right? So now the question is, well, what is the value of y right here? Okay, so value of y right here, this box has a width of 1, right? So box number 1 has a width of 1. This is equal to 3. You might say, okay, wait, how do you know that this is 3? Well, I tried to make it so that this top of the box crosses the line right in the middle of that interval in there, right? So right in the middle, 1/2. If I go up here and I plug in 1/2, I will have 4 minus 1, and that'll equal 3, right? Now I'm going to do the same thing with this box, right? So that box also has a width of 1. And if I were to look at what this side is, right? So I'd go and plug in 3/2 up here. And I would say, all right, plug in 3/2. Okay, that's going to be 4 minus 3. Oh, that's equal to 1. All right, so now the area, my approximate area for this, let's see, do this in green. My approximate area is going to be the area of this box plus the area of this box. All right, so what am I going to have? 3 times 1, right, plus, and then 1 times 1. Oh, all right. Okay, not consistent notation in there. All right, so I'm saying that my area is round 4. Right? Okay, so now to get the exact area, let's get it precise. Let's see. I go like this. I'm going to keep my feet here. Is one of the things I like about when you've got on video, you don't erase the board. All right. So the precise answer to this, again, this is a triangle. You could go in and do just your old school geometry analysis on it, but we're in calc class now. So if we want to get the precise area is going to be equal to the indefinite integral over the interval that we've got there, 0 to 2, of y dx, of the integrand is going to be that 4 minus 2x, right? Integrated over x like that. All right, so if we calculate the area, notice here I'm not saying approximate. This is precise. Right, so I'm going to go, all right, I've got 4x, then minus x squared. And so, and then that evaluated from 0 to 2. Okay. All right, so, all right, then what do? I go in and I say, all right, I plug in 2. So I've got 8 minus 4. And then I subtract off my endpoints. So this one, again, I chose 0 for this one. And so this is just basically 0 minus 0. We're just subtracting off 0 in this particular case. And what do you know? I get 8 minus 4, I get 4. All right. Now with a line, what that means is because they're like, wait a second, you put approximate over here, you put equal over here. With the straight line, what that meant is when I set this up, the amount that I overshot over here was just canceled by the amount that I undershot over here. And the amount that I overshot over here was canceled out by the amount I undershot over there. And so with a line, it actually worked out nice and perfect. All right. But we need to try something that has some curvature to it. All right, so let's go ahead and try something. So we're going to do it with a parabola. I'm going to make it a little bit trickier parabola, but we'll do that. And then we have got our start on section 6.3. Okay, so let me start with the parabola. And let's go with, all right, what if y is equal to, I am going to go with 4 plus 2x squared. All right, and I'm going to do that from 0 to 2. Okay, so this is a parabola. This x squared is your standard parabola. I've got it actually augmented by a factor of 2, and I've also got it shifted upward by an amount by 4 units here. So if I were to graph this out, I'm going to do careful graph of this. So here's x, here's y. And we're going to calculate the area underneath it. Right now, I'm going to be a little bit careful here. Let's see. Let's stay. Okay, let's do this in blue. Okay, so I'm going to have 1 and 2. And so here's 1/2. Here is 3/2. Okay, and so I am considering interval from 0 to 2 in here. And if I were to plot this out, so I am going to go up here and I'm going to say, all right, if I were to go, okay, so if I were to go 1, 2, 3, 4, 5, etc. in here. Now I were to plot this out at 1/2. If I go and I plug in 1/2, okay, the scale, I needed to make that a little bit bigger. But if I were to go to plug in 1/2 into this, if I were to plug in 1/2, I would have 1/4 here times 2. This would be 1/2. And so I'd be up at, so I'm going to fudge this a little bit. I almost really shouldn't have put a scale on here as I think about it, right? But my graph would be up at 4.5. Right? So ignore that scale there. And if I were to go to 3/2, my parabola would be up at, this would be 3/2, 8.5 up here. And so if I were to graph it out, it would be a curve that does, so starting out at 4, it would look something like that. So I'm just graphing that out. And the one thing I put on there as a point is I put a point in this, because I'm going to break this up into 2 subintervals, 2 Riemann sum boxes from 0 to 1, 1 to 2, and I'm taking the midpoint in each of those, and I have graphed out where those are. Right? So if I were to take a box that goes through the graph at that midpoint of 1/2, I end up with a box here. Right? And notice I'm overshooting a little here, I'm undershooting a little here. Then I'm going to do the same thing with my second interval. All right, so again, I am overshooting here, I'm undershooting here. Now it's not going to work out as perfectly as it did. It's not going to work out as perfectly as it did with a line, because it's not linear. And so this is truly going to be an approximation. Okay, so if I calculate my area for this, all right, so my area under the curve between 0 and 2 is going to be approximately equal to the area under of box 1 plus the area of box 2, where box 1, that is a rectangle where one side is 4.5 and one side is 1. So with that one, I'm going to have 1 times 4.5. For my second one, I've got an area where one side is 1 and the other side is 8.5, like so. All right. So my approximate area for this is going to be around, so what have I got here? 4.5 plus 8.5. That is basically going to give me 13. All right, so my approximate area using this concept of these approximate boxes in there. If I use two of them, it tells me that my answer is 13. Now, that worked out perfectly with the line. It's not going to work out perfectly with the parabola, but it'll be close, right? So, and the more boxes I use, the smaller those widths are, the better my approximation. But if I go to the precise limit on this, in other words, if I say, well, what if I do more and more boxes, I get a better approximation. Well, let's just go directly to precise value. So, right. So if we go to the precise area, what are we doing? We are going to the indefinite integral from 0 to 2 with our integrand being y. We've got over here integrating over dx. Again, so that dx is what we did here is we took the width times the height. The dx is the width. The 4 plus 2x squared is the height. And the fact that we were adding them up, but we're doing the integral means that we are adding up an infinite number of those boxes. Have an infinitesimally small little slice dx times the height of the curve at that particular point. And this is adding up an infinite number of rectangles. And the rectangles are infinitesimally thin. They're not zero, they're infinitesimally small. It's a weird concept. All right, so let's do the integral on this. Again, this is a definite integral. We do not have to worry about the constant. So I'm going to have 4x. And then I've got 2x squared on this. And all right, so when I take the integral of this, I am going to have 2. Be a little bit deliberate on this. I'm going to go 2. And then I am going to go, all right, x squared is going to be x cubed over 3, like so. And I am going from 0 to 2. Right? And so my area is going to be, let me do a little cleaning up of it, 4x plus 2/3 x cubed from 0 to 2. And by the way, eventually we're going to get to where we don't necessarily have to have one of the endpoints be 0. I'm doing that for convenience at the moment, but we're going to branch out. But what I do is I go and I plug in. So I take the first value, one up at the top. Oops. So if I want to plug that in, 4 times 2 plus 2/3 times 2 cubed. All right. Then minus, I'm going to subtract off. Well, that's 0. That's 0. Okay, so that's nice and easy. If I were to do a different endpoint, then I would just plug something different in. Key thing you got to notice though is that when you subtract off, you're subtracting off the entire thing. So that negative sign would distribute in there. When it's 0, it doesn't end up mattering. All right, so let's see. What do we got here? All right, so I have got 8. And what have I got here? So 4 times 2. Here I've got 8 because I've got 2 cubed. So 2 cubed, 8 times 2. I've got 16/3. Let's do a little fractional math here. So let's get a common denominator for these two. So if they're going to have a common denominator, 3 is going to be a good go-to on that. I'll try to keep this in the shot there. So I'm going to have 24/3 plus 16/3. That is going to be equal to, all right, 32/3. All right, so now 2/3, 40/3. Did the wrong thing and didn't think about, okay, 20, so 24 plus 16 is going to give us 40/3. All right. Now, if we do this in on our calculator, we get an answer of 13.3 repeating. If we do it in terms of just in terms of fractions, 3 goes into 39 13 times, so we'd have a remainder of 1/3. These two numbers are equivalent, but these are precise answers. So how did we do? Actually, not all that bad with this, but I would argue the nice thing about this is this you can do to any how function, no matter how complicated. This is cumbersome. Once you get good at integrating, this is much easier to do. But look, we were actually only off by 1/3 in 13 parts in there. So that's actually not too bad. And however, the funkier, the more complicated your function is, using two boxes for a lot of functions, that just doesn't work out to be that great an approximation. In the end, who cares? If we can take the integral of it, we can actually calculate it precisely like that. And that's what we just did. All right, so a little recap on the concept of area. So we were thinking of calculating the area by making these boxes, this concept of the Riemann sum in there. And so this is a length, a height times a width. And that width, we made it infinitesimally smaller, making an infinite number of boxes that basically end up being just lines across there and adding up all the infinite number of these, and it adds up to the finite area of the curve. And all right, that's what we got. So we will pick this up again at the next session.